Thank you. Good morning, everybody. My name is Camilo Vasquez, and today I'm going to talk about our work on real-time speech-driven avatar animation by predicting facial landmarks and deformation blend shape. I will start with a brief introduction about our work. So the motivation behind speech-driven avatar animation relies on the fact that modern animated movies and games rely on expressive facial animations to convey emotions and to enhance storytelling. In particular, vision-based facial animation is very expensive. It requires complex hardware and also the presence of the actors that are not always available, especially when reshoots have to be done. On the other hand, speech-based facial animation is way cost-effective because it doesn't require the physical presence of the actors and it doesn't require these complex cameras. We also can use speech-driven animations using text-to-speech synthesis systems. So you can generate also animation using artificial data to animate, for instance, large-scale personas during games. So it's important when using speech-based animation not only to perform accurate lip sync, but also to transfer the emotions of the actor into the avatars. When talking about speech-based facial animation, we have two different paradigms or two different type of systems. On the one hand, we have these large-scale neural models that are able to produce high-quality animations. However, since they can be very complex, they are not suitable for real-time application during live events. In this case, we have models based on diffusion or these large-scale transformer networks. On the other hand, we have models based on BSM recognition that are able to produce faster animations. However, they lack emotional expression and intent transfer. There are several challenges when talking about real-time animations. Current systems, as I previously mentioned, are based on large-scale transformer models and diffusion systems that are not able to produce high-quality animations in real time during live events or during interactive events with public. There is also a limitation in software compatibility. It is very difficult to integrate existing architecture, existing system in professional animation engines like Unity. So combining these two challenges, we see that there is a need for an efficient and solution that is able to produce high quality animations in real time and that is able to be compatible and integrated with professional animation softwares. So the contribution of our work relies on, we propose a novel real-time speech-driven avatar animation engine to bridge the gap between high fidelity visuals and smooth interaction, especially designed for interactive and live events. We consider different deep architectures to generate several animation representation types in real time, including particularly different facial landmarks and ARkit deformation blend shapes. Our models are evaluated both objective and subjectively in order to check not only the errors and the accuracy of the proposed models, but also perceptual quality indicators about emotional transfers, quality, and lip sync. Finally, we create an extensive evaluation about the different runtime capabilities that are essential in order to animate avatars in real time during production live events. Now, regarding our methods, let's start with the facial animations that we aim to animate. First, we have the traditional 2D facial landmarks that correspond to 68 points that represent different aspects of the face, in this case. Then we have the 3D facial landmarks. In this case, is a superset of the previous one. We have 478 X, Y, and Z coordinates that are able to produce avatar animations in 3D. And finally, we have this deformation ARkit Blendshapes that corresponds to 58 coefficients to model different muscle deformations in the face geometry of an already existing avatars. In this case, we can modulate the movement of the mouth, the movement of the eyebrows, the eyes, the cheek, among others. Regarding the different models that we consider, our purpose, as I previously mentioned, is to produce speech-driven animations in real time. This is why more complex architectures are not considered. So we rely only on these three simple models. First, we have an LSTM network that is used as baseline. Then we have a simple 1D CNN that processes the raw speech signal, is able to create or to predict these facial landmarks and the 52 coefficients for the blend shapes. And third, we have a signet model that also processes the raw speech signal, use signet filters and 3 convolutional layers to predict the different animation representation types. Finally, we create a client-server application using FFmpeg with and WebSockets for real-time audio stream processing. In this case, a client sends a continuous audio stream to the server that buffers them until it has enough data. In particular, we process windows of 280 milliseconds and predict facial animations for the central frame, in this case, a frame of 40 milliseconds. Each predicted animation is sent back to the client for visualization and integration with animation engines. In this way, we guarantee a continuous stream of animation at an average 25 frames per second and a maximum delay of 280 milliseconds. Now, regarding the data description that we consider here, we consider 2 different data sets. On the one hand, we have an emotional corpus, the CREMA-D data, that is commonly used for speech emotion recognition applications. We have utterances and recordings in 6 different emotions: anger, disgust, fear, happiness, neutral, and sadness, from 91 different speakers. On the other hand, we have a neutral corpus, the GRID corpus, which is designed for multimodal audiovisual speech recognition. In this case, we have only neutral utterances from 34 speakers. Now, regarding some results in the prediction of each animation representation type, we have first the prediction of the 2D landmarks. We evaluate different error metrics. We have the landmark distance and the landmark velocity distance. In this case, watching the prediction of the errors in the prediction of the landmarks, we observe that the 1D CNN and the signet achieve significant lower error rates than this LSTM baseline. On the other hand, for velocity metrics, we observe that the baseline model exhibits lower error rates. However, this is kind of expected, considering that the baseline is a recurrent model that is able to model better these temporal dynamics. Finally, we observe that models perform better at predicting facial landmarks for neutral faces, in this case with the GRID corpus compared to the CREMA-D emotional corpus. Now, regarding the prediction of the 3-dimensional landmarks, we observe that errors are higher than those reported for the 2-dimensional case. This is also expected, considering that this is a way more complex model that has to predict more than 10 times points compared to the previous one. In this case, we observe that the CNN model surpasses the signet with a statistically significant lower errors. Finally, regarding the evaluation of the deformation blend shapes, we evaluate the mean average error for different parts of the face. We observe that the cheek and the jaw areas are the most accurately reconstructed, are the most accurate to animate. On the other hand, we observe that the eyes and the eyebrows are the most challenging areas to animate and to predict the blend shapes. So, in addition to the objective evaluation, we also perform a subjective test. In this case, the emotional 1D CNN model is used to generate 40 animations using 2 different avatars, this yellow one and this gray one. We consider independent audio samples recorded by an actress, and 23 external participants rated the videos in 4 different categories: the expressiveness, the coherence, the global quality of the animation, and the lip sync quality. Each video received scores from 1 to 5. On average, we have scores between around 3.5. We observe that the perceived quality depends on the selected avatar. We assign higher score were assigned for the yellow avatar compared to the gray one. Finally, the evaluation of our real-time capabilities. We have a separate client and server connected via Wi-Fi, and we transmit a 1 hour stream from the client to server. We were able to produce real-time animations at 25 frames per second with a minimal latency, and we observe a average real-time factor of 0.07 for each of the 3 animation types. Now, to conclude my talk, we propose a novel approach to produce facial animations in real time, specifically designed for interactive live events and virtual spaces. We consider different configuration of facial representations, including 2-dimensional, 3-dimensional landmarks, and ARkit Blendshapes. Our models were evaluated both objectively and perceptually by external users, and we showed that it was possible to generate animations at a constant rate of 25 FPS with a relatively low latency and delay. So for future work, we would like to improve the quality of the generated animations to make them more natural and expressive. The main limitation here is that we couldn't use a large corpora with more varied emotions, linguistic diversity, and demographic variability. So this is everything from my side. Thank you very much.